Hello students, in a series of applications of uniform circular motion, this is our third video. In this video, we are going to discuss conical pendulum. Now let's understand what is conical pendulum. A simple pendulum which is given such a motion that the bob describes a horizontal circle and the string describes a cone. In a given GIF, you can see student, the bob describes horizontal circle and the length of the pendulum describes a cone. Now let's find out what are the forces acts on the conical pendulum. For that, we consider a bob of mass m. Here we consider the mass of a bob as a point mass. L be the length of the pendulum. The length of the pendulum is a measure from the point of suspension to the center of gravity of the bob. The bob describes horizontal circle of radius r and revolve with the speed v. H be the actual height of the cone described by the string. Theta is the semi-vertical angle between the height of the cone and the length of the string. Let T be the tension in the string. Tension acts along the string towards the support, that is towards fixed point. Mg is the weight of the bob which acts vertically downwards. Now student, here we are not consider the weight of the string because the selection of a string for the conical pendulum should be such that it is inextensible and light-weighted. So here we have to just consider the weight of the bob. Now let's resolve the tension T. This is the vertical component of the tension. As you can see in the diagram student, the vertical component of the tension and that of the height of the cone both are parallel to each other. And the length of the pendulum is the intersecting line of these two parallel lines, so that the angle between the T, that is the tension, and its vertical component is theta. This vertical component is a T cos theta. This vertical component T cos theta balances weight of the bob. Now let's see the horizontal component of the tension, which is T sin theta. As you can see student, this T sin theta is directed towards the center of the circle. Hence, this T sin theta component of a tension provides necessary centripetal force for the revolution of the bob. This T sin theta component balances the centrifugal force. Hence, we can write T sin theta is equal to mv square upon r. Now students, let's find out the formula for the semi-vertical angle. For that, we consider equation T cos theta is equal to mg and T sin theta is equal to mv square upon r. Divide equation 2 by equation 1. We have a T sin theta divided by T cos theta, which is equal to mv square upon r upon mg. Now cancel common term. So cancel tension and that of a mass of the bob. We have sin theta divided by cos theta as a tan theta, which is equal to v square upon rg. Hence, theta, that is a semi-vertical angle, is equal to tan inverse v square upon rg. Now students, let's find the tension in string. For that, we again consider the same equation T cos theta is equal to mg, T sin theta is equal to mv square upon r. Now student, we need to square and add equation 1 and 2. So we have T square sin square theta plus T square cos square theta is equal to mg square plus mv square upon r whole bracket square. Now we write 2t square is equal to mg bracket square plus mv square upon r whole bracket square. It is because student, we can use the identity sin square theta plus cos square theta is equal to 1. Now student, let's give this equation as equation number 3. In the previous slide, we find the formula for the semi-vertical angle tan theta is equal to v square upon rg. In the given diagram, we can see student tan theta is equal to r upon h. So as LHS of the both these equations are same, RHS also have to be same. So we can write r by h is equal to v square upon rg. That is v square is equal to r square into g divided by h, which is equation number 4. Now students, substitute this equation number 4 in the equation number 3. After simplification, we have tension in the string T is equal to mg under root of 1 plus r by h whole bracket square. Now let's find out the period of a conical pendulum. For that, let's consider tan theta, which is equal to v square upon rg. But we know, student, speed of the pendulum v is equal to 2 pi r upon t, where the t is the period of the pendulum. Now, student, note down here the symbol t is used over here is for the period, which is different from that of the tension symbol. Now, substitute this value of a speed in the above equation. We have a tan theta equal to 4 pi square r square upon t square rg. After simplification, we have a period of the conical pendulum t is equal to 2 pi under root of r upon g tan theta. Now, let's substitute the value of r, that is L sine theta, in the given equation. We have a period t is equal to 2 pi under root of L sine theta divided by g tan theta. So tan theta is a sine theta divided by cos theta. The tan theta get cancelled. Ultimately, we have equation for the period t is equal to 2 pi under root of L cos theta divided by g. From above equation, we can see, student, period of a simple pendulum depends upon length of the pendulum, acceleration due to gravity, and the semi-vertical angle theta. Now let's understand one case for which the theta is very small. When the theta is very small, cos theta is approximately 1. It is because, student, for the cos 0, we having the value 1. And that's why when the theta is very small, the value of a theta is closer to 1. So let's substitute this value of a cos theta in above equation. We have a period t is equal to 2 pi under root of L by g. So as you can see, student, in the given formula, there is no value of a theta. From this, we can see, student, period is independent of theta. So the period of a pendulum is independent of a theta only when the theta is very small. Now, student, let's find out the frequency of a conical pendulum. We know, student, the relation between the frequency and that of a period. Frequency n is inversely proportional to period. Therefore, the formula for the frequency is equal to 1 upon 2 pi under root of g upon L into cos theta. Now, student, let's understand what is the effect of an increase in speed on the conical pendulum. In the given diagram, you can see, student, the same pendulum describes different cone. Why this is happening, let's understand. For the understanding, let's consider a conical pendulum revolve with the speed v. Here in a diagram, you can see the different forces act on the bob. Now let's consider the weight of the bob is 0.2 Newton and the tension in the string is 0.5 Newton. So to balance weight of the bob, the t cos theta should be of 0.2 Newton. So remaining 0.3 Newton is used by the t sine theta to provide the necessary centripetal force. Here, note down, student, mg, that is the weight of the bob, is fixed. Therefore, vertical component t cos theta, which is equal to weight of the bob, is equal to constant, which is never changes. From this, we can say, student, the tension T and that of a centrifugal force are variable forces which is depend upon the speed of a revolution. Now let's consider the second case in which the bob is revolved with the speed greater than that of a v. Here in this case, what happens, student, when the speed of a revolution increase, centrifugal force increase, which tries to pull the bob away from the center of the horizontal circle. Because of that, you can see here, student, the radius of the horizontal circle increase, that of the height of the cone decrease, and the semi-vertical angle also increase. So in short, we can say, student, with the increase in speed, centrifugal force increases, which increase the radius, semi-vertical angle of the cone and decrease its height. Now, in order to balance this centrifugal force, tension in the string increase because the tension in the string provides the necessary centripetal force for the circular motion. So here you can see, student, the magnitude of a tension is increased. Now let's suppose this magnitude of a tension is a 0.6 Newton. As we already discussed, student, weight of the bob is a 0.2 Newton, which will not change even there is a change in speed. So the vertical component required to balance this weight is also 0.2 Newton. So even though the tension and that of the semi-vertical angle changes, but the ultimate value of a t dash cos that theta should be of a 0.2 Newton. So the remaining value of a 0.4 Newton is used by t dash sine dash theta to balance the centrifugal force. From all this discussion, you can understand, student, the tension is a self-adjusting force. It adjusts itself with the increase or change in speed. But note down here, student, the tension has a certain limit up to which it can increase its value. So the maximum possible tension for the given speed is known as a breaking tension. Beyond this, if you increase the speed of the bob, the string will get break. Now let's compare the period of revolution. As you can see, the same pendulum describes different cone with the different speed. Let this bob revolve with the speed v and this above bob revolve with the speed v dash. Obviously, the speed v dash should be greater than v as it describes large circle. Let t be the period of a pendulum which revolve with the speed v, which is equal to 2 pi under root of L cos theta divided by g. And the period t dash is equal to 2 pi under root of L cos theta dash upon g. Here note down, student, the length of the pendulum is same, but the semi-vertical angle is different. So from this comparison, you can write the period t dash is less than that of a t. It is because as speed increases, the period decreases. Now let's understand what is the effect of a semi-vertical angle on the conical pendulum. Case 1, let semi-vertical angle is equal to theta. Here, the mg weight acts vertically downward and the tension acts vertically upward. As these two forces balance each other, there is no possibility of the bob to describe cone. So here there is no conic motion can possible for this pendulum. Now let's consider the second case where the semi-vertical angle is equal to 90 degree. Here in the diagram you can see, student, semi-vertical angle is a 90 degree. This bob describes a horizontal circle with the radius equal to the length of the pendulum. T is the tension in the string which provides necessary centripetal force and balance centrifugal force mv square upon r. And the weight of the bob acts vertically downward direction. As you can see here, student, there is no component of the tension which balances weight of the bob. So t cos theta in the given situation is 0. So according to Newton's law, mg remain unbalanced. So unbalanced force, that is mg, pulls the bob downward until the tension T gives the vertical component, that is T cos theta, which is equal to mg. From this you can understand, student, the conical pendulum cannot have the semi-vertical angle equal to 90 degree. The same is true for the sling also. So student, I ask you to think over and write in a comment box. Hope you understand the concept. Do like, share and subscribe my channel. Thank you.